So as we look to understand this quantum model of the atom a little bit better about where these electrons are, we have sort of two big questions that we need to answer. The first one is, why do atoms have energy levels? We know from the evidence we get from elements' atomic spectra that they must have energy levels, because there are only certain regions in which the electrons, only certain energies the electrons can have and no energies in between, but we don't know why they have these energy levels. And then the second question that we need to answer is, how exactly are the electrons arranged around the nucleus? We may know they're in energy levels, but we don't really know where they are. So there are two big discoveries that are going to give us the answers to these questions. The first one is that electrons, like photons, exhibit wave-particle duality, that tendency to both have particle properties and wave particles simultaneously. The second piece of information that we're going to talk about in this lesson is that for this sort of particle that has both wave properties and particle properties, it's impossible to determine both the exact position and the exact momentum of the particle. And specifically, what's going to be important here is that we can't find the exact position. And so that's going to tell us a little bit, even though it seems like it would actually tell us less, but that's actually going to tell us a little bit about where these electrons are in the atom. So, in 1924, Louis Dubois hypothesized that electrons and other particles of matter, like electrons, have both the properties of particles and of waves. And so Dubois felt that Dubois felt that electrons were sort of like photons. You know, we said that they're both simultaneously a particle and a wave. They have both properties at the same time. So a few years after this, there were some experiments that were done, I think around 1927, that proved him right. What they basically did is that they took some electrons and they took a beam of electrons and they sort of fired that beam of electrons, if I can get that to actually right here, so fired that beam of electrons towards a metal plate, and that metal plate had two slits in it. Now, normally, if you fire things through something like this, you fire particles through something like this, you should just get a nice spread distribution out here. There'll be more of them sort of towards the center, and then there'll be less and less as you get sort of farther out from it. But that's not what happened. Is that instead, they basically got what you're seeing in this picture down here, is that the electrons formed this, what's called an interference pattern. And this little animation that you're seeing down here is sort of showing how the electrons showed up. There were a lot of electrons in a few spots right in here, but then there were other spots where there were no electrons hitting at all. And this is a property of waves. Waves tend to produce interference patterns like this when you shoot them through two nearby slits like you're seeing up there. And so let's look at that. So the reason why is that one property that waves have is that they interfere with each other. And so what this means is that if you take two waves and you overlap them, you shine them over the top of them, there are two ways that this can happen, or there are multiple ways that this can happen, but there are two important ways. One is that whenever you overlap these waves, is that they could overlap so that they line up. There are peaks of one, so here's one wave. When we add it to another wave, the peaks of one line up with the peaks of the other wave. And then whenever you do that, what you end up with is you end up with a wave, when we add those two up, that's going to be a stronger wave. You know, so whenever there are peaks here, there's a peak here. Whenever there's a trough, there's a trough. They sort of reinforce each other. And when that happens, that's called constructive interference. But the other thing that can happen is, what if the peaks don't line up? What if they're exactly opposite to that? That our first wave looks like this, but then our second wave that overlaps it is like exactly backwards from it. Whenever that happens, you get what's called destructive interference, because that wherever one has a peak, the other has a trough. And so if you add those up, what do you get? You get zero. And whenever this one has a peak, the other one has a trough. You add that up, what do you get? Zero, because one's positive, one's negative. You get no wave at all whenever that happens. And so these are sort of our two things that can happen with waves. And so whenever you get patterns, like the one that we're seeing in this particular diagram, they shot the electrons through the slits, would tend to indicate that at the spots that have little blue lines on there are where the electron waves, their peaks added up. And so we got electrons in that location. But at the red spots that we're sort of showing in here, where there are no electrons, that would mean that the electron waves had a peak where another electron wave from the other slit had a trough, and they just canceled out. You don't have to know the details of how this works, but what's important is just knowing that if you have a particle that also has wave-like properties, that they can sometimes add up, the waves can sometimes add up, and they can sometimes cancel out. And so if this is true, You know, if electrons do act as waves as they move around the atom, then they would only be able to exist where there was constructive interference between the electron waves, because anywhere else there'd be destructive interference. It would cancel out the electron waves and there would be no electron there at all. So this explains energy levels. If the electron wave overlaps itself perfectly, then the interference is constructive and the electron can exist there. So that's basically what we're showing sort of in this picture right here. So we have sort of a general distance, that's the black line on here. The red line is the electron wave. And so in this case, this is sort of a wave that's exactly the right wavelength for it to sort of eat its own tail. So the wave might start here, it goes up and around, it goes up and around like this, and then it's exactly lined up so it overlaps itself. So every single wave, as the electron moves around the atom, adds to it, makes it stronger and stronger. And so this is a stable situation. An electron could exist in this particular configuration. But over on our other side, over here, this is one where the wave doesn't exactly line up on itself. And so if we were to start tracing this around, we get something that looks a little bit like this. So the first wave goes around. So far so good, but then what happens? Oh, now it doesn't line up with itself. And so now, as it goes around, we're getting some cases where it just sort of overlaps itself very, very poorly. And so if you notice, if I were to keep going like this, eventually this would just fill up every bit of space on here. At every spot that the electron wave had a high spot, there would also be a corresponding low spot. And so we would end up with destructive interference. This whole thing would just cancel out. There would be no possibility for the electron to be there because the electron wave would cancel itself out. So this is something that you might run into that would happen inside an atom if electrons are waves. And since we do know that electrons are waves, that this would explain why we have energy levels. Just to give you another illustration of sort of how this would work. So here we have an atom. And so in this particular case, the nucleus is like right here. And so you see n equals 1. That's first energy level. So in this sort of flattened atom situation, in reality, atoms of course are three-dimensional, not two-dimensional like this, is that the wave goes around and then bites its own tail like this. That's a constructive interference. At n equals 2, that's our second energy level. You can see the wave travels around here, goes around the circle, bites its own tail, and so another constructive interference. In between those two spots, though, all the waves will not bite their own tail. You will not have them overlap each other where the peaks line up the peaks every time. So you're going to have destructive interference. The electron, therefore, cannot exist between our first energy level, n equals 1, and our second energy level, n equals 2. Third energy level, you can see that whereas the first one was one sort of quick little wave circle, the second one, it's almost like the wave had two peaks on it. In the third energy level, now the wave has 3 peaks as it goes around, before it once again goes around, bites its own tail, the wave lines up so every time it goes around it always hits the same spots all over again. Where it had a peak the first time around, it has a peak the second time around, in the third time, in the fourth time, in the fifth time. It never is in a spot where it can cancel itself out. So this explains why we have energy levels in the atom. So that's our first piece of evidence. Our second piece of evidence we have here is in 1927. Werner Heisenberg said, hey, if you look at wave-like particles, you know, like the electron that we saw before that's existing as this electron wave, since it's a wave, it really can't exist at one particular location. I mean, you can't say that a wave is in one spot. It sort of fills up a whole space. And so he came up with some math that basically showed that for this type of wave, it's impossible to know exactly both the position of a particle that's both a particle and a wave and its momentum. And in fact, that the more precisely you know its position, the less precisely you know its momentum. And so this means that if you know more about where the particle is, you know less about its momentum, how fast it's going. But if the more you know about how fast it's going, the less you know about exactly where it is. And this is not a measurement problem. This is not something that if we just had better technology, we'd be able to do this. This is a fundamental property of the universe, of these particles. The problem is that in the atom, for the electron wave to fit one of these wave patterns like this, there has to be at least some information there about what its momentum is. And because there's at least some information about the momentum, that means we can't know what the position of that electron is exactly. All we can do is just say it's within a certain region. So this is sort of what we discovered here. The position of the electron in an atom would always be to some degree uncertain. We can't know exactly where it is. And so because of the fact that it's uncertain where this electron is, this idea that Heisenberg came up with is called the uncertainty principle. This idea that you cannot know exactly the location of the electron in the atom. All you can basically do is say that we know where it is in a certain region or the likelihood of finding it in a certain place. So as we sort of said, if you know the wavelength of the electron, it tells us something about the electron's momentum, so the best we can say is that an electron at each energy level is most likely to exist in a certain region. And so if we want to show that, like say, well, where is the electron then? We can't say exactly where it is, but we can describe what's called a probability density or probability distribution for the electron, something that says that, hey, this electron is likely to be in this location, even if we don't know it's exactly here. We might say, hey, there's a 50% chance of it being in this region, or an 80% chance, or a 99% chance of it being in this region. And we can do that because that's something that there is enough math to be able to calculate that here. So a probability density shows the region where the electron is most likely to be, but never where it is. And the term for this region, where you're most likely to find this electron, is called an orbital. Okay, so it's based on the word orbit. Remember, Bohr's model had this idea that electrons were orbiting the nucleus, but they're not actually orbiting it here. Instead, they're in these regions of probability called orbitals. Now, I know this is a little hard to visualize, so let's take a look at one way that we could visualize it here. So we have three different pictures of the same orbital here. And so our first picture, number one, is basically showing a probability distribution for one particular electron orbital. Okay? So the way this works is that you really may not be able to see it on your screen, but there are a bunch of little dots that are in here. And the dots tend to be a little denser. They're closer together in like this region and this region, and they're farther out in this region and this region. And then out here, there are almost no dots at all. So way out here, outside these areas, you're really not seeing much of anything in terms of those dots here. And so what those dots indicate are not the locations of individual electrons, but those dots indicate basically where are the electrons most likely to be found. The heavy concentration of dots means the electron is most likely to be found in that location. Lower concentrations of dots means it's less likely to be found in those locations. So one way we can sort of take that sort of dot probability diagram is we can take it and we can sort of draw over sort of some really sort of lobes that are over the top here. These sort of regions of space, and this would be three-dimensional. It looks two-dimensional here, but imagine this is three-dimensional. And these lobes that we draw out here might say, hey, there is a 90% chance of finding the electron inside those two lobes. And so we sort of turn them into some three-dimensional spaces, and that's what it's showing down here, is imagine these are sort of these three-dimensional lobes that are out here. They call them balloons for this one right here. They represent the region of space where there would be 90% chance of finding this particular electron. So we can't say exactly where it is, but we can say there's a 90% chance that it's in this region right here. And this is just one particular example of an orbital. There are lots of other orbitals that are out there, lots of other orbital shapes, and we'll look at those in more detail a little bit later. So this is sort of how it works when we're talking about this idea of an orbital. So we can't determine exactly where the electron is. So as a result, we say the general region where all electrons are is the electron cloud. We've used that term before. We said electrons are in the electron cloud. Well, why do we call it a cloud? We call it a cloud because we don't know exactly where those electrons are. But we do know that they're in a certain region. And so we could say that, hey, if the nucleus is right here, that there is a 90% chance the electrons are all in this region right here. Imagine this is spherical. I can't really draw a sphere on this, but imagine that this is a sphere surrounding that, or it may be some different shape other than a sphere, but we can basically say that those electrons are found in that region. So it's more of a probability cloud than it is an actual sort of fluffy cloud. So within the electron cloud, the particular region where it's most likely to find each individual electron is determined by two things. Okay? And so remember, those particular regions are called orbitals. So there are two things that determine what the orbitals or where you're going to find each electron here. So number one is if the electron waves constructively interfere and are stable. Okay? That's where we talked about the energy level, because they can't exist in places where those waves destructively interfere, where the waves don't line back up with them. So that's number one. Number two is the location where these waves constructively interfere. The picture that we sort of showed right here, this particular distribution is really just a mathematical solution for a three-dimensional wave that constructively interferes. That's why it has this particular, somewhat weird looking, but this particular shape. Other shapes that you look at whenever you look at these orbitals, of correspond to other cases of constructive interference of waves. So an electron orbital shows a particular electron's probability density, which is the region in space where you're most likely to find that particular electron. So if we looked at this, here's another example of some orbital shapes. So these are sort of some weird, different looking ones here. In this case, these are all part of of orbitals that are part of a certain shape called a D type of orbital or D shape of orbital. So if you look at these, that like our first one here indicates that the electron has a 90% chance of being in these sort of orange lobes that are in here. And for that particular electron, that's where it would be. Now, a different electron might not be in that particular orbital. A different electron might be in this orbital, which if you look at it shape-wise looks a lot like the first one. It's just oriented differently. So you can see that the first one is sort of oriented along the YZ axis. This one right here in the second picture is oriented along the XZ axis. And then the last one has the same shape, but it's oriented along the XY axis. And so you can sort of see how that works here. Now the very last one is even weirder. It's sort of got this ring around it. But each of these shapes is basically one set of three-dimensional waves, constructive interference locations. The reason why it has those particular shapes is because those are the ones that particularly constructively interfere. The same way that for this diagram right here, why does it have this particular sort of three peaked shape right here? Well, in 2 dimensions, that's the reason why is because that's where the waves constructively interfere. In 3 dimensions, they look a little weirder because it's got 3 dimensions instead of 2. But still, this would be an example of orbital shapes. And we'll look at a little more detail at these later on. So, at this point, we now have 2 rules about the electrons and atoms. The first rule is that electrons and atoms can only have certain energies called energy levels, which is determined by the places where the electron waves constructively interfere. Second rule is that electrons and atoms don't have exact locations, but we can describe the probability of finding an electron in a certain region, and that certain region is called the orbital.